Hi guys, this is Jenna Gaspari, and I did my project on exponential growth of bacteria, specifically talking about E. coli virus. Alright, just to give a little background on exponential growth, which is basically growth that increases by a constant proportion, I'm going to be using two equations that will demonstrate this. So our first one is going to be F equals I times 2 to the power of n, which demonstrates how bacteria divides by a constant minute. In E. coli's case, a single bacterium divides every 20 minutes. In this equation, F is used to demonstrate the final number of bacteria, I is the initial, or the number of bacteria that we started with, n being the number of generations, which is actually the total time for the division, divided by the taken for one division. The second equation we're going to be using is P equals P of 0 times e to the power of r times t. In this equation, P is the total population after time, t. P of 0 is the starting population. E is a constant number which can be found on your calculator. R is the percent rate of growth, and t is the time. These two equations will give you the same resulting number, but are used differently depending on what information you were given. Alright, now that we've touched on exponential growth, let's talk about bacteria. So bacteria are a type of biological cell. They constitute a large domain of prokaryotic microorganisms. Bacteria are usually typically a few micrometers in length and were among the first life forms to appear on Earth and are present in most of its habitats. Bacteria are classified into 5 groups according to their basic shapes: spherical, rod, spiral, comma, and corkscrew. They can exist as single cells in pairs, chains, or clusters. One particular type of bacteria is E. coli. E. coli is a species of bacteria that inhabits the stomach and intestines. When it is in contaminated items such as water, milk, or food transmitted through a bite of a fly, it can cause gastrointestinal illnesses. Each daughter cell is a clone of the parent cell, so when conditions are favorable, meaning the right temperature and all nutrients are available, the E. coli bacteria can divide every 20 minutes. Here are some examples of what the different shapes look like. Now that we know a little bit about exponential growth and the bacteria we're working with, we're going to be answering 3 essential questions. Part 1, given this information, find the initial number of bacteria. Part 2, find the rate of growth as a percent. And Part 3, if a single E. coli culture doubles every 20 minutes and the culture increases exponentially, how many hours until it reaches 262,144 bacteria? How many bacteria will there be after 1 hour and after 1,440 minutes? Now on to Part 1. Knowing that when conditions are favorable, E. coli can divide every 20 minutes, you are able to calculate that in just 7 hours there will be 2,097,152 bacteria produced. Now, given this information, we're going to find the initial or starting number of bacteria. Using the formula F equals I times 2 to the power of n, you're able to figure this out. It should also be mentioned that n, which is the number of generations, must stay consistent throughout the problem. Therefore, since you're given a 20-minute division, t should be converted to minutes as well. You do this by multiplying time given, which was 7 hours, by 60 minutes. And as a side note, it's also important to know that the generation time equals the time interval required for cells, or population, to divide. You can start by filling in the final number of bacteria with the 2,097,152 number you were provided. Next, in order to find n, you must remember that n is actually t divided by the time it takes for one division. In this problem, you know that each division happens every 20 minutes. You also know what's happening in 7 hours. But since we need to convert that to minutes, you can do 7 hours times 60 minutes, which gives you 420 minutes. Therefore, you find that n equals 420 divided by 20, which equals 21 generations. Next, we're looking for I, which is the initial or starting population of the bacteria. So once you plug in F and N to the equation, you can calculate 2 to the power of 21, which equals 2,097,152. Your next step is to divide each side by this 2 million number, and then you find out that the starting bacteria amount was actually one single bacterium. Therefore, you have now found that a single bacterium will produce 2,097,152 bacteria after 7 hours. So as you can see from this information, you were able to create a base equation using all of your information, which shows us that n equals t divided by 20, and I will always be 1. And here we see that the graph shows exponential growth. Now that we've completed part 1, let's go on to part 2. Use the information previously given and find the growth rate as a percent. You can do this by using the second equation given earlier on, which stated that p equals p of 0 times e to the power of r times t. We can begin by filling in the information that we already know, starting with e, which, as mentioned before, is a constant number located on your calculator. Next, we can add that the total population, or p, equals 2,097,152. We can also add that p of 0, which is the starting population, equals the 1 bacterium we found from the first equation. Last, we can fill in t, which needs to be thought of in minutes. It is actually the 20-minute division that we are given in the initial set of information. Now to find the rate. When finding r, you have 2 ways to think about it. We know that a single bacterium divides every 20 minutes. With that information, we can conclude that after 40 minutes, there would be 2 bacteria, 60 minutes, 3 bacteria, and so on and so forth. Therefore, we can set up an equation assuming that if we started with 1 bacteria and our t equals 20 minutes, our final bacteria will be 2. Once those numbers are plugged into the equation, we know that in order to get rid of the e on the right side, we must take the natural log by using the power property of logarithms. This then cancels out the e on the right side, but leaves the natural log on the left side. Using our calculator, we can find out what the natural log of 2 is, and then divide it by 2 that is left on the other side. We then find that r equals 0.034657. The second way we can do this still uses the same equation, but just requires a little more converting. In this case, we can enter the 2 million number that was previously given into the final population spot, but instead of using the 7 years for t, we must convert that to months, again by multiplying it by 60 and getting 420. Therefore, the equation now reads 2,097,152 equals 1 times e to the power of 420 times r. Next, we take the natural log of each side in order to cancel out the e on the right side. Again, use your calculator to find the natural log of 2,097,152 divided by 420. This should give you the same resulting rate growth as the last problem, which was 0.034657. This means that the rate of growth for 2,097,152 bacteria in 7 hours is 3.47%. As you can see, after using both equations, we have the same model of this exponential growth graph. Now on to part 3. For this, we would like to find out how many hours it will take for the E. coli to reach 262,144. We can see on the chart that the starting population is 1 bacterium. For this problem, we are looking to find t, and again we have 2 options. The first option uses the f equals I times 2 to the power of n equation. We can fill in the 262,144 into the f spot, and you must remember that n actually equals t divided by 20. Once we fill it in, we can see that this equation is in exponential form, but in order to find t, hopefully we remember that we need to find the inverse of the equation and switch it into log form. Once we do this, the equation will read log base 2 of 262,144 equals t divided by 20. Then on our calculator, we can find log base 2 of 262,144 and multiply that by 20. This gives us about 360, but we know that it is in minutes, and the chart is asking for hours, so we can divide that by 60, therefore getting us 6 hours. The second way to solve this is by using p equals 1 times e to the power of r times t. You can use either equation and you'll get the same answer. But for this, we need to remember to use the previous growth rate we just got, which was 3.47%, but turn this back into a decimal. Fill in the final number of 262,144. Again, we need to take the natural log of each side, canceling out the e. Insert into your calculator natural log of 262,144 divided by 0.034657. which will again give you 360. So we divide by 60 and get 6 hours. Now we can fill in the chart. We can first put 6 hours and also fill in the growth rate. In fact, we could save time and fill in the same starting population of 1 bacterium in all the spots, and also the same growth rate in all the spots. We know all these will be the same for each problem. Next, we're trying to find how many bacteria there will be after only 1 hour. It is the final number we were looking for this time, which is f. So our equation, when filled in, will be f equals 1 times 2 to the power of t divided by 20. But we know that since we're looking for the amount after 1 hour, we can multiply this by 60 to get 60 minutes. Therefore, 2 to the power of 60 divided by 20, or 3, will give us an ending population of 8 bacteria. Now, using the second equation, we can fill in our 3.47% rate in decimal form, and of course remembering that t must be in minutes, so t is actually 60. So we can simply calculate e to the power of 0.034657 times 60 and get an answer again of about 8 bacteria once we round. Now we can just fill in the 8 bacteria into our chart. Although this specific question wasn't asked, we can see that the next slot to fill on the chart is missing time after 6 hours and before 24 hours. So we can use the given f of 6.87 times 10 to the power of 10 and our initial number of 1. Our equation should read 6.87 times 10 to the power of 10 equals 1 times 2 to the power of t divided by 20 to solve for the missing t. Again, we need to take the inverse of the exponential equation, putting it into the log form. So log base 2 of 6.87 times 10 to the power of 10 equals t divided by 20. We can then multiply each side by 20 and get a t answer of 720 minutes, which will be about 12 hours. If we would prefer to use the equation with growth rate, we can fill it in as follows. 6.87 times 10 to the power of 10 equals 1 times e to the power of 0.034657 times t. Once we take the natural log of each side, we can calculate the natural log 6.87 times 10 to the power of 10 divided by 0.034657 will give us a similar t, when rounded, of 720, then divided by 60, that gives us 12. We can now fill in the 12 hours into the missing spot. Lastly, we can see that even though the question is asking to find the total population after 1,440 minutes, we can calculate that the number divided by 60 and realize we are looking for the last spot of 24 hours. Since we're looking for the missing f, we can fill in as follows: 2 to the power of 1,440 divided by 20, and quickly see that the final population is 4.72 times 10 to the 21st power. Or instead, we can insert our growth rate and 1,440 onto the other equation as e to the power of 0.034657 times 1,440 and get an estimated answer of 4.72 times 10 to the power of 21. Once we fill in that last number, assuming that you filled in as we went along, we can now see that the table is complete. As mentioned before, both equations give us the same exponential growth graph. On this graph, I decided to add a few coordinates we found from the given information in the table. But since it didn't go as high as some of our larger populations, I also added that at 90 minutes the population would be about 22.63 bacteria, and at 120 minutes it would be about 64 bacteria. Hopefully now you have a better understanding of exponential growth used in the real world. Thank you for listening.